Welcome back to the deep dive. If you've ever designed a network, you know that moment of truth isn't just getting devices connected, it's making sure they can actually talk to each other when they live on different virtual networks. So today, we are cracking open the network design playbook for inter-VLAN routing.
And it's really the foundational puzzle of modern networking, isn't it? Crossing that chasm from layer 2 up to layer 3. Our mission today is to, well, analyze the configs and the trade-offs for the four main ways engineers get IP packets to route between subnets on separate VLANs.
Okay, let's unpack that crucial separation first, because this is where the whole problem really starts. You've got your VLANs at layer 2. They create separate broadcast domains. Basically, they're like virtual switches inside your physical switch. And then you have your IP subnets at layer 3, which is all about your addressing.
Right, and here's the core conflict. A standard layer 2 switch, its only job is to forward frames inside a single VLAN. It just looks at MAC addresses. So if a frame needs to jump from, say, VLAN 10 over to VLAN 20, that layer 2 switch, it just can't do it.
It has no idea what to do.
Exactly. It'll just drop the frame. Its world ends right at that broadcast domain boundary.
So bottom line, if you want any communication between these different domains, you have to bring in a layer 3 device. That could be a router or one of these multi-layer switches. Something has to do the actual IP routing.
Absolutely. That layer 3 device becomes the default gateway for every single VLAN that needs to talk to the outside world. It sits in the middle, looks at the destination IP, and says, okay, you need to go out this door to get to VLAN 20.
So we've got 4 ways to solve this, and they kind of represent an evolution from, simpler hardware setups to these big integrated cores. Our roadmap today covers router on a stick, then SVIs on layer 3 switches, layer 3 routing ports, and finally those routers that have switch ports built right in. Let's start with the classic, maybe the most budget-friendly one, router on a stick, ROACE.
ROACE is definitely the go-to for smaller sites, branch offices, that kind of thing. The whole idea is you leverage a router that's probably already there for your WAN connection, and you just make it pull double duty for local VLAN routing.
The name itself, router on a stick, it suggests a very specific physical setup. So if you've got that one single cable connecting the router to the switch, that's the stick, how does that one connection handle traffic for, 5 different VLANs?
Well, it does it by turning that physical link into an 802.1q VLAN trunk. So the router has one stick going into the network. But inside the router's brain, we create what's called a subinterface. It's a logical interface for each and every VLAN. We're basically chopping that stick into a bunch of logical segments.
Okay, and this is where the config gets really specific, right? You're telling the router which little logical segment belongs to which VLAN.
Precisely. You create these virtual subinterfaces like G00.0 for VLAN 10. And the magic command, the one that makes it all work, is encapsulation.1q and then the VLAN ID. Once you run that, the router knows, okay, I should expect tagged frames for VLAN 10 on this subinterface.
And that subinterface is where you put the IP address. That becomes the default gateway for every device in that VLAN.
Correct. Now, here's a little detail our sources brought up that trips up a lot of new engineers.
Right.
Well, you would name the subinterface 0 for VLAN 10, just to keep things clear.
For your own sanity.
For your own sanity, yes. But the subinterface number and the VLAN ID are totally independent. You could technically use subinterface 0.99 for VLAN 10. It's the encapsulation.1q10 command that actually does the work.
That is a great tip for when you inherit someone else's messy network. Now, what about the native VLAN? That's the one VLAN on the trunk that doesn't get a tag. How does the router handle routing for that one?
The router gives you a couple of choices. The first way is you can just put the IP address directly on the physical interface itself, no subinterface. The router just assumes that's for the untagged native VLAN. Or you can still use a subinterface, but you have to add the native keyword to the command. So encapsulation.1key, your VLAN native.
Okay, so ROS is cheap. It's flexible. But relying on that single physical stick, that sounds like it could be a performance bottleneck for sure, but also a huge troubleshooting blind spot. Where's the big risk?
The bottleneck is very real, yes. All your inter-VLAN traffic is squeezing through one link. But you're right, the blind spot is so much worse. If you set up the router side perfectly, those subinterfaces will show up as long as that physical cable is plugged in. The router has almost zero visibility into the layer 2 health of the switch it's connected to.
So the router could be sitting there thinking, yep, I'm a perfect gateway for VLAN 30, but over on the switch, VLAN 30 might not even exist. Or maybe the port isn't even a trunk, and the router is just happily routing packets into a black hole.
Exactly. That is the ROAS dilemma. You have to remember, your layer 3 routing plane is completely dependent on a layer 2 config that it can't see. So your first troubleshooting step is always cross-checking. Check the routes on the router, sure, but then immediately jump to the switch and verify the VLANs in the trunk port.
That sets us up perfectly for the next method, which really tackles that performance and consolidation problem head on. If using an external router is the slow point, the next logical step is to bring that routing function right into the switch itself. And that's where layer 3 switches become the engines of big campus networks.
It's a massive shift. We go from external routing to internal routing. A layer 3 switch, or a multi-layer switch, it combines layer 2 switching and layer 3 routing in one high-speed device. This is what you see in the core or distribution layers of a network where you just can't afford a bottleneck.
And this brings us to the heart of it. Switched virtual interfaces, or SVIs, they do the exact same job as the ROAS subinterfaces, but they're virtual interfaces created inside the switch itself. They're the internal gateways.
The configuration is actually pretty simple, but the dependencies, they can be tricky. First thing, and this is a classic mistake, you have to enable the layer 3 function globally with the eater routing command. If you forget that,
You just have a very expensive layer 2 switch.
you have a very expensive layer 2 switch.
Exactly.
Once that's on, you create the SVI with interface VLANed, and then you give it an IP address.
Okay, but unlike a physical port that knows if a cable is plugged in, an SVI is totally virtual. How does it decide if it's actually functional, if it should be up and routing traffic?
Yeah, this is where it gets interesting. It relies entirely on something called auto-state logic. It's on by default. And this is basically the switch running a little internal health check. For an SVI to get to that beautiful up state, it has to pass a whole checklist of dependencies.
A checklist is good. Walk us through it, because this sounds like it could be the biggest point of failure in a core network.
It really is. So 4 things must be true at the same time. The first 2 are easy. The VLAN has to exist on the switch, and it can't be shut down.
Okay.
The third is that the SVI interface itself, interface VLAN 10, also can't be shut down. Just basic admin stuff.
Right, those 3 are just about making sure you've configured it to be on. What's the critical 4th one?
The 4th one is the big one. The switch has to have at least one physical interface. Could be an access port or trunk that is currently up and is assigned to that VLAN. This is the failsafe. It ensures the routing engine doesn't start forwarding packets to a network segment that has no live devices on it.
Wow, so it's not just checking a cable, it's checking the actual pulse of the entire VLAN. So if I have 100 devices in VLAN 40 and the very last one gets unplugged, the SVI for VLAN 40 just goes down.
Immediately, it transitions to down, and that stops all routing to that subnet from other places. It's designed to prevent blackhauling traffic. If you, say, delete a VLAN with no VLAN 40, the 1st and 4th requirements fail instantly, and the SVI goes down.
That dependency is so crucial to understand. Okay, let's move on to the other routing method on these switches.
Okay.
Routed ports. When do you pick an SVI versus a routed port?
This is a key design choice, and it's all about topology. You use an SVI when you're the gateway for a whole broadcast domain with lots of hosts. You use a routed port when you just have a single high-speed point-to-point link, usually connecting to another router or another layer 3 switch.
So with a routed port, we're taking a physical switch port and telling it to forget everything it knows about layer 2 and just be a router interface.
We are stripping all of that away, yes. Yeah. And you do it with one simple but really powerful command on the interface. No switch port. As soon as you type that, the port sheds all its layer 2 logic. It won't do VLANs anymore. It will now accept an IP address directly.
And this idea is essential for scaling up connections with layer 3 ether channels. Why would we want to bundle multiple of these routed ports together?
Redundancy and simplicity. Imagine you're connecting a core switch to a distribution switch with, say, 4 parallel links. If those were all separate routed ports, your routing protocol, like OSPF, would see 4 separate paths. You'd have to build 4 neighbor relationships, and your routing cable gets bloated.
So the goal is to trick the routing protocol into thinking those 4 physical links are just one big logical pipe.
Precisely. You create an L3 ether channel, and the bundle acts as a single, logical, routed link. The routing protocol only sees one neighbor over one interface. It cleans up the routing table and gives you much smarter load balancing across the links.
So the config has to combine the ether channel process with the routed port process. How do you make sure the IP address goes on the right interface?
It's a 3-step process. First, on all the physical member ports, you need the no switch port command, and then you assign them to a channel group. Second, the port channel interface you create, interface port channel 12 or whatever, that also needs the no switch port command.
That seems a little redundant. We already did it on the physical ports. Why the port channel too?
Because the port channel is its own logical thing. You have to explicitly tell it you are a layer 3 interface. And third, this is the most important part, the IP address and mask go only on the port channel interface, not the physical members. The IP has to live on the logical bundle that the routing protocol is actually going to talk to.
That makes sense. And I'm guessing just like with layer 2 ether channels, all the physical links have to match their settings perfectly.
Oh, absolutely. The consistency checks are very strict. Every physical link in the bundle has to match on the no switch port setting and also on speed and duplex. Any mismatch, and the link won't join the bundle.
Okay, that brings us to our last method, which is really the ultimate consolidation. VLAN routing on a router's integrated LAN switch ports. This is the all-in-one box.
Exactly. This is for that small branch office that needs a WAN router and, 4 or 5 local LAN ports, but they don't want to buy a whole separate switch. We're talking about devices like the Cisco ISRs, the smaller Catalyst models.
So from the outside, it looks like a normal router, but internally, it's running the logic of a layer 3 switch to handle traffic between its own local ports.
That's a perfect way to put it. It uses the exact same SVI logic we just talked about. You use its internal switching hardware to assign ports to VLANs, then you create SVIs to be the gateways for those VLANs, and it routes traffic between them and out the WAN port.
So it's a 3-phase config. Set up your VLANs and ports, create your SVIs with IP addresses, and then configure your normal routed WAN port.
Correct. The big point of confusion for a lot of people is just figuring out which physical port is a switch port and which one is a true routed port on these boxes.
Is there a quick CLI trick to tell them apart? They can look identical?
There is a great one, the command show interfaces status. This command will only list the physical ports that are configured as layer 2 switch ports. It'll completely omit the traditional routed ports. So it's a super reliable way to see which is which.
That is a genuinely useful tip for when you're troubleshooting. And if that fails, I guess you can just try to configure them. A switch port will take switch port access LAN, but reject IP address. A routed port is the opposite.
The command set will always tell you the truth. If you try to put an IP on a switch port, it'll just give you an error right away.
This has been a really complete tour of that L2 to L3 transition. We hit all 4 methods, each with a very different purpose. ROAS for the budget-conscious, SVIs for high-speed campus cores, routed ports for point-to-point links, and the integrated router for the small office.
And the takeaway for you, the designer, is that all 4 of these tools get you to the same end goal. They route between broadcast domains. The choice is purely strategic. It's driven by scale, by budget, by performance needs.
We started this deep dive talking about that ROAS blind spot where layer 3 thinks everything's fine but layer 2 is broken. Let's end with a final provocative thought that goes a little beyond just the command line.
The auto-state logic in a layer 3 switch forces the SVI down if layer 2 fails. That's a system built on high trust, tying the fate of layer 3 directly to layer 2. But when layer 3 routing is external, like with ROAS, and it just reports up no matter what, it brings up a bigger question. In any large, robust network, how much trust should one layer ever place in the reported status of the layer directly beneath it?
Something to think about the next time you're building out a segmented network. That's all the time we have for this deep dive.